Hi everyone, in this video I'd like to show you what I've been working on over the last few years. This is a major update to my asmSynth library for Arduino, and it brings a number of new features and improvements. The biggest change is that waveform can now be created and added dynamically while the program is running. In the previous version, oscillators and their waveform types had to be defined at compile time, which meant they couldn't be changed later without modifying and recompiling the code. Another major addition is a built-in real-time operating system. This allows multiple tasks to run independently and simultaneously, which is essential for features such as low-frequency oscillators that modulate other oscillators, as well as background melody playback. Having an RTOS also opens the door to many other applications beyond audio synthesizers, including game development and other multitasking projects. A standalone version of this operating system, which I also developed, is available on GitHub under the name Objective RTOS. You will find the link in the description below. Further videos will be coming soon, so make sure to subscribe if you don't want to miss them. But for this video, I'd like to focus on showcasing the project and demonstrating what it can do. In the default configuration, the audio output is generated on PWM pin 3, so all you need to do is connect a speaker between that pin and ground. For this demonstration, however, I'm using a little later configuration. Here is what the PCB looks like. Ironically, the sound quality is actually better with a simple PWM output than with the resistor rider. The resistor tolerances turn out to be too high, and they simply not precise enough to produce clean and clear audio without introducing noticeable noise. Because of that, I probably designed another board based on PWM instead. The library supports very different output configurations, and I'll be covering them in much greater detail in future tutorials and in documentation. Let's start with a simple example. Here we have a function called melody, which is responsible for playing a short piece of music. To play a note, we simply create a new piano object. There is no need to worry about memory management. The object automatically destroys itself once the sound has completely faded out. The delay task function pauses the current task for a specific amount of time, while rerun task restarts the task from the beginning. To have the operating system execute the melody function, all we need to do is create a task object and pass a pointer to that function. Okay, let's upload the program to the board. By the way, it's funny how it sounds when a program is uploaded to a microcontroller. As you can see, the entire program takes up only about 3 kilobytes of memory. Based on my testing, it's possible to run up to 16 polyphonic voices at roughly a 20 kHz sample rate, which is a very impressive result for hardware of this class. You will be able to see the audio waveform and CPU usage in real time, as well as how the Arduino handles the workload while generating audio. At the bottom of the waveform display, you can see the current sample number. The counter is advancing incredibly fast. That's a 20 kHz sample rate in action. Keep in mind that all of this is running a microcontroller clocked at just 16 MHz. Here's what the result sounds like. Just to show that all of the audio is being generated directly on microcontroller, I disconnect the Arduino from my laptop and run it from a power bank instead. I can even change the power source for the speakers, and everything keeps working exactly as before. The sound is being generated entirely by the Arduino. This example focused on performance. We'll see how many simultaneous voices can be played at once and what impact that has on CPU usage. This example demonstrates that it's possible to create a wide variety of instrument sounds, including ones based on sine waves. The flute sound you hear will use additional tasks as well. The sine wave is frequency modulated to create a natural vibrato effect, making the sound feel much more realistic. Creating drum and percussion sounds is just as straightforward. It's also possible to run multiple independent melody tracks at the same time whenever needed. This can be especially useful for games, where music and sound effects often need to be generated independently from one another. All that's required is another task function and another task object pointing to it. This capability is made possible by the built-in real-time operating system. Let's listen to a few more sounds examples. And finally, here's the last example. Thanks for watching. I most likely continue developing this project, and one of the features I'd like to add in the future is a fully functional speech synthesizer. The goal is to create a library that takes up only around 5 kilobytes of memory, while being capable of generating spoken messages directly from text. If you'd like to see that happen, be sure to leave a like. There will be plenty more content related to this project coming to the channel soon, so don't forget to subscribe if you'd like to stay up to date with future videos. Thanks again for watching, and I'll see you in the next one.